In this lecture, let's look at this example of polynomial function. First of all, we need to explain why the graph shown below could be modeled with a polynomial function f. Then what can you conclude about the degree and the leading coefficient of f? Then find a possible equation for f of x. By looking at the graph, we notice that the function is smooth and unbroken. Furthermore, the graph does not have a vertical asymptote nor a horizontal asymptote. From here, we can conclude that this function could be modeled with a polynomial function. Then the next step is to find a possible equation for this f of x. Let's first notice some properties of this graph. We notice that both ends, both pointing in the same direction, they both point upward. This polynomial function has an even end degree. Furthermore, since the ends are pointing upward, so the leading coefficient, an, is positive. Then we also notice that this graph has 3 roots, which means the degree of this function is at least 3. Then, the graph has 3 local extrema, 3 turning points, which means the degree of f is at least 4. Because remember from the theorem, a polynomial function of degree n, then it has at most n-1 local extrema. So if we have 3 extrema, that means the degree is at least 4. We can also get that from the first 2 points. The second point says the degree of f is at least 3. But from the first point, we know that n has to be even, and the smallest even number above 3 is 4. So the degree of f is at least 4. Then from the graph, we note that the roots is at x equals to -3, -1, and 2. Note that the 2 is a repeated root, because this root happens at one of the local extrema. So around x equals to 2, the function looks like another quadratic function. So we call this root the repeated root. Then from this information, I can set up a model for this polynomial function. F of x will be in this form. Some coefficient in front, a, times the first linear factor corresponds to the root at x equals to -3. So x plus 3. Then the next root is at x equals to -1. So its linear factor is x plus 1. Then we have a repeated root at x equals to 2. So I'm going to square this linear factor, that is x minus 2, and this square. Then the next step is to find the coefficient a. We can find this a by substituting any point from the function except the roots. For example, I can take the y-intercept. From the graph, I note that the y-intercept is at y equals to 6. So let's substitute this point, x equals to 0 and y equals to 6 into this model. So I'm going to substitute the point. Sub the point with coordinates 0 and 6 into the f of x. So f of 0, that is a times 0 plus 3 times 0 plus 1, then times 0 minus 2 squared. And this equals to f of 0, which is 6. Then I can isolate for a. On the left-hand side, I have a times 3 times 1 times 4, that is 12, and equals to the right-hand side, 6. So the coefficient a is 1 over 2. Now I can write out the possible equation for this f of x. F of x could be 1 over 2 times x plus 3 times x plus 1, then times x minus 2 squared. This is a polynomial of degree 4, so we can call that a quartic polynomial function. And that is the end of the lecture. In the next lecture, let's look at an example of rational function.